Hello students, welcome to lecture 5 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on overview of metamaterials technology. Here is the lecture outline. We will briefly look into metamaterials in history, discuss about the evolution of metamaterial technology with the help of a market study. We will see how metamaterials technology feature in different consumer sectors such as medical, automotive, aerospace. Okay. We will also talk about metamaterial fabrication techniques such as photolithography, shadow mask lithography and electron beam lithography, just to tell you and give you an idea of how things are actually made. So, the origin of metamaterials can be traced to various historical examples such as pyramid brick walls, the columns of the Parthenon, medieval ruby glass and also twisted jute fibers. So, these are basically early examples that have significantly influenced the conceptual foundation of metamaterials in contemporary technologies such as communication, imaging, sensing, stealth and quantum devices. Through the use of frequency selective surfaces, electromagnetic band gap and other related innovations. Okay. So, these are the frequency selective surfaces and this is electromagnetically programmable band gap structures. So, in 2016, there was a market study that basically presents the worldwide metamaterial market, and the estimate showed that the market size in 2016 was around 316 million. But in the recent days, there has been an increasing requirement of better quality parts with durability properties. So, that has also fueled the growth of metamaterials medium market worldwide. So, the Grand View research has classified this worldwide metamaterial market associated with end use, different regions, okay, product and finally based on their particular usage, which you can see from this particular figure. So, what do we see that if you consider end use, different sectors like automotive, medical, military and electronics, these are the domains where metamaterials are used. Region wise, mainly in Asia Pacific, India, Japan, China, North America and also Middle East, South Africa, it has got a huge market. According to the product, if you think of metamaterials, there is a big segment in electromagnetic metamaterials, photonic, then there are tunable metamaterials and nonlinear metamaterials. And majority of the applications are focused towards absorber, metamaterial antenna design, cloaking devices and making super lens. So, in 2014, the global metamaterial market size was valued at $1 billion US, right? And if you see that that is 2024. Now, looking forward, the metamaterials market is projected to reach $6.9 billion US by 2033, right? So, that has basically going to exhibit a growth rate or CAGR of 23.31% over 2025 to 2033. So, currently North America is dominating the market, holding a share of around 42% in 2024, and here also you can see the colors representing different sectors such as electromagnetic metamaterials, then you have terahertz metamaterial next, you have the photonic metamaterials, different tunable metamaterials, frequency selective surfaces and other applications. Okay. So, all are growing, and as you can see, terahertz and photonics metamaterials are also going to be equally prominent in the market as the other RF or microwave metamaterials. So, the market is primarily driven by technological advancements in nanotechnology and photonics, increasing demand in wireless communication and defense sector, expanding the applications towards also healthcare and sustainable solutions, okay, educational and research initiatives and different customization potential across various industries. Every industry requires a metamaterial or a material where you can tune the property of that material based on your application, and that is where the metamaterial market is basically catering to. Now, aerospace and defense lead the market with around almost 30% of the market share in 2024 that you can see from here. Next comes the medical, automotive, consumer electronics, energy and power, and different other applications. Okay. So, the use of metamaterials in aerospace and defense sector is pivotal. These particular industries, okay, metamaterials can be used to enhance the capability of the communication systems, radar, and also make the stealth technology feasible. Their unique properties enable the development of advanced antennas and radar systems with improved performance, reduced size, and increased frequency bandwidth. So, they are also very critical in stealth technology, which is a very important technology in today's world, aiding in the development of materials that can effectively reduce the radar cross section of any aircraft or missile. So, this application is key for modern defense strategies that rely on minimally detective or detectable technology. Medical sector is one of the important sector as well, where the prominent applications of metamaterials are mainly towards efficient wireless power transfer for implantable medical devices. So, Lee et al. Introduced an advanced wireless power transfer augmented with a negative permittivity metasurface, or you can call it as mu negative metasurface MNG, which is tailored specifically for biological applications. So, this miniaturized wearable device is positioned directly on the human skin, and it incorporates a negative permeability metasurface that basically increases the power transfer efficiency. So, this is how it looks like. So, if you zoom this, okay, you will see that this is an external transmitter coil, okay, and then here is your implantable receiver antenna, okay, and before the antenna you are basically putting, so this boundary marks the skin, this is your metasurface. So, what happens, the team basically embeds a dual band receiver just 3 mm beneath the skin, capable of simultaneous power transmission through the lower band. Typically, they were using 402 megahertz to 405 megahertz, and the data transfer via the higher band, okay, that is between 1.6 gigahertz to 2.4 gigahertz. So, this was used for power transmission, this was used for data transmission. So, here I can show you the unit cell they used. So, this is basically a double sided 5 turn spiral mu negative metamaterial unit cell, okay, and the metasurface was basically having metamaterial or metasurface, do not get confused, metasurface is just a 2D version of the metamaterial. So, here you can see the MNG metasurface has basically a overall dimension of 30 mm by 30 mm, okay, by it has got an array of 3 by 3 unit cell that is fabricated on a F4B substrate with dielectric constant of around 2.65, okay, and the design parameters, here you can see that this particular length is 10 mm, A is 4.6 mm, B is around 9.4 mm, SL, the gap between the lines, around 0.2 mm, width of each line is around 0.4 mm, and T, which is basically, and T is around 1 mm. So, to ensure seamless wireless power transfer or power connectivity, they utilize a conformal strongly coupled magnetic resonator coil as transmitter. Okay, here is also another clear experimental setup shown. So, this is basically the transmitter. This is a skin mimicking gel. So, you have got a mu negative metamaterial placed on top of the skin, and just beneath the skin you have your receiver, right. And remember, this is got a dual layer. Okay. So, the dual layer induced current basically increased the metasurface, which was transmitted to the receiver side. Okay. So, that is how it worked in charging the implantable medical devices through wireless power transfer. Wang and all, another group, they also introduced a new wireless power transfer system by integrating it with miniaturized metasurface to enhance the wireless power transfer efficiency and extend the lifetime of the implantable devices. So, in their wireless power transfer system, you can see the metasurface element, the dimensions are 10.5 mm on both sides and thickness is 1 mm. Okay. And this is the front view, or you can say top view, and this is the bottom view. Similar kind of orientation, but here the metasurface is basically a group of 4 elements, a 2 by 2 array. Okay. And the overall size was 21 mm by 21 mm by 1 mm is the thickness. Okay. And D, this distance is taken as 50 mm, right. So, it is similar kind of a system. So, this is the transmitting antenna, this is the overall wireless power transfer system. You have got a implantable antenna. Okay. So, this one, there is a metasurface on top of the skin, so that allows you a better power transfer. So, in this case also F4B is selected as the substrate, which has got a dielectric constant of 2.65, and the planar reverse spiral structure, this one is implemented on the both side. And what do we see, that this MNG metasurface or mu negative metasurface has a strong magnetic resonant behavior, which can improve the efficiency of the wireless power transfer system. And when you integrate such metasurface array, that basically improves the power transfer efficiency and effective transmission distance, even with the human body's inherent absorption capabilities. In the automotive sector also, metamaterial technology is playing a crucial role. So, recently there is more requirement of a new material in the automotive field, where you want high performance magnetic and absorbing as well as shielding material, so that you can operate the motors with electricity and ensure their electromagnetic compatibility. Okay. So, the performance, absorbing and shielding materials are needed to ensure electromagnetic compatibility, right. So, in addition, many more materials like photonic metamaterials can also enhance the capability of automobile optical devices. So, Toyota Central Research and Development Lab, they reported that metamaterials provide high contribution in the use of automobile, such as in the areas of mobile communication antennas, radar scanning. New magnetic metamaterials can be used for applications of electric motors, and the use of industrialization will include early stage applications such as driving applications and other applications like tire pressure monitoring systems, EMC body application, etc. So, if you want to see the overall view of metamaterials where they feature in this automobile field, you can say that they basically come under radar, laser radar, motor magnetic materials, okay, EMC body, okay, then small antennas, night vision system, LED headlight. So, these are the different places in automotive sector where metamaterials are going to play a very important role. One example of metamaterials can be towards this physiological monitoring in a real life driving scenario. So, here you can see metamaterials can be used to show the accurate heartbeat detection with a median interbeat interval IBI detection error of around 23.5 millisecond during driving. So, what they do, you can actually make a embroidered metamaterials, so which comes along with the seat belt. Okay. So, you can put that in a way that when the driver puts on the seat belt, the driver's physiological parameters, okay, gets constantly monitored. So, it will allow you to detect very minimal fatigue and drowsiness. So, this is the structure that is shown here. So, you have different parameters like h equals 16 mm and p, the pitch around 10 mm, a is around 4 mm and g is 5 mm. So, these are all done on a substrate which consists of a polyester fabric. So, permittivity is roughly 1.5 and overall thickness is around 1 mm. So, what it is done, the sensor, this is basically the sensor that monitors your heart rate, and this sensor is attached to the center of the seat belt at the subject's thoracic region. So, it should be here close to your heart, okay, and connected to a lightweight software defined radio using coaxial cables. So, the metamaterial basically supports confined microwave surface waves that are modulated by subtle or very minimal local physiological motions which are sensitively transmitted or transduced into changes in the phase of the transmitted signal, right. So, that allows you to kind of provide early warning system that if the driver is going to have drowsiness or he is going to feel fatigue, so that any accidents in future can be avoided. In the aerospace sector, metamaterials have emerged as a transformative materials, okay, which can offer unprecedented control over the electromagnetic, acoustic and mechanical properties. Their engineered structures enable innovative solutions for lightweight design, improved stealth capabilities, that is minimal detection, metadomes, vibration damping, thermal management and advanced communication systems. So, the commercial market for metamaterial based components and subsystems in aerospace and defense are projected to reach approximately $250 million by 2020, and by 2025 it is supposed to become a $2.3 billion market. Okay. So, here you can see that as the demand increases, okay, with times like people are looking for high performance multifunctional aerospace components where metamaterials will play a critical role in shaping the future of aviation and space exploration as well. But this particular figure tells you how metadome is going to work. Okay. So, metamaterial absorber application will be very important in the stealth technology when you want to go undetected and target your enemies. Okay. So, what is important that your metamaterial which is giving you the stealth technology is also protected from external force like wind pressure, bird strike and adverse weather conditions, and still it remains undetectable by the radar signals. So, the illustrated metadome not only enhance broadband radar absorption, rather it will also protect the structure from external environment. So, you can see that the structure basically consists of a metamaterial absorber, or you can say metasurface absorber, and then it has got a dielectric metadome both with a FR4 substrate. So, the top layer is basically giving you the physical or mechanical protection, right. So, the metadome structure has broadband absorptivity in addition to its protecting properties and polarization insensitivity. So, this is a typical structure. So, you can see T1 and T3 are typically 2.4 mm, T2 is 0.4 mm, this particular period. So, this is basically the side view, this is the top view of the structure. So, A is around 14 mm, the length L equals 3.2 or 3.02 mm, R is around 4 mm, B is 0.5 mm, C around 0.35 mm, and R1 is around 150 ohm, right. So, what is important here to see that the structure roles as structural roles as absorber. So, this particular one works as an absorber, okay, the one with this unit cell design. So, that is basically your metasurface absorber, and the dielectric one, the dielectric metadome gives you the protection from the external environment. So, this is how overall the structure looks like. Okay. So, this dielectric metadome allows the signal to get in, but then it is this particular metasurface absorber allows broadband absorption, which is also angle insensitive, and that is how it is giving you a very little scattering signature. Now, experimentally, when the performance is evaluated, so this is the absorptivity graph versus the frequency, and these are for different angles. Okay. So, you can see that for the normal case, so this is the normal incidence case, you can see that for 0 to 90 degree absorptivity is almost around 90% over the range from 4.8 to 14.4 gigahertz, right. And when the metadome is subjected to oblique incidence, you can see that it is showing angle insensitivity from 0 to around 40 degree in the case of TE mode, and in this case for TM mode it gives you angle insensitivity from 0 to 60 degree, right. That is how the metadome performs. Now, with that let us move on to some overview of the metamaterial fabrication techniques. We will just briefly talk about those. So, the first technique is photolithography, that is a technique for microfabrication which can be used to synthesize metamaterials that work at terahertz frequencies. So, this technique has been commonly used in making single and multi-layer metamaterials, since it is able to fabricate high resolution sub-wavelength structures at wavelength range of 30 micron to 3 mm with minimal complications. So, here is some of those results. So, it shows a multi-layer fishnet metamaterial developed using microfabrication process on PDMS. So, PDMS is basically polydimethyl siloxane. It is a popular silicon polymer with wide variety of use, from cosmetics to industrial lubrication to passive daytime radiative cooling. So, here the resonators were first patterned in metal. So, 200 nanometer gold thin films were used with adhesion layers. They were deposited on spin coated PDMS substrate post curing. Curing is the process of toughening it. Okay. So, often microscale resolution patterns obtained by these techniques are further encapsulated by a thin layer of PDMS to avoid delamination of the metallic layers. So, what are the steps involved in photolithography? So, you can see that the fabrication of a multi-layered flexible terahertz metamaterial can start with a bare silicon substrate as a sacrificial wafer, okay, and then a polyimide solution was spin coated onto the substrate, and then it was baked at 180 degree centigrade in a convection oven for around 30 minutes to give you a flexible metamaterial substrate, okay, like this. Then a negative photoresist was spin coated and patterned using conventional photolithography. So, this particular figure shows you the unit cell structure of a high index metamaterial made of a thin eye-shaped metallic patch. So, this is a eye-shaped metallic patch which was symmetrically embedded in a dielectric material, and this is typically the optical micrograph of the fabricated single layer metamaterial. So, this shows the time scale, okay, sorry, the length scale or the bar. So, what is done, that repeating the polyimide coating and the curing process, okay, before that. So, gold chromium, this the thickness 90 and 90 mm and nm and 10 nm was then evaporated, and then it was patterned as shaped array structure, and then you are repeating the polyimide coating and the curing processes, you can end up making this single layered metamaterials. So, the curing process basically, as I mentioned, it hardens or toughens, okay, through a chemical reaction or a physical action, right, resulting in a more stable substance. The curing of polyimide layers were conducted at around 350 degrees centigrade using an open-ended quartz tube furnace under an inert atmosphere to convert the polyimide acid into a fully aromatic and insoluble polyimide. So, multi-layer metamaterials on silicon substrate can also be fabricated in the same way by repeating the process that you have seen for the single layered one until the desired number of metamaterial layers are basically stacked, and finally, a flexible terahertz metamaterial can be fabricated by peeling off the metamaterials from the silicon substrate. So, here as I mentioned, in this particular simulation we consider the light to be falling from the top, okay, with polarization shown like this, okay, and here you can see the higher magnification micrograph of a 2 layer and a 3 layer metamaterial, and this shows you the flexibility test of the fabricated metamaterials. The next method is called shadow mask lithography. So, it is basically acid free fabrication technique employed to create planar and multiple layer micro and nanoscale features. So, this technique involves direct deposition onto a substrate through a stencil. So, I will show you the figure, yeah, these are the stencil. So, during the deposition of thin metallic film or oxides without the need of any photolithography or etching processes. So, this is analogous to screen printing approaches that are utilized to fabricate t-shirts, right. So, a stencil is first prepared, which is made of through substrate, etching on a silicon wafer or an aluminum foil, and then the stencil is placed either in direct contact or in close proximity of the substrate. Subsequently, the metallic or dielectric patterns as required will be deposited predominantly by electron beam evaporation to utilize the inherent line of sight deposition method that creates a basically 1:1 copy of the stencil onto the substrate. So, you can see that the bow tie patterns through the openings of this stencil is basically created on the substrate. So, using this shadow mask lithography, feature as small as 100 nanometer wide can be patterned on arbitrary substrates including polymers and plastics, they are which are basically mechanically fragile and or they are chemically sensitive. Okay. So, you can see that you can come up with this kind of patterns on them, right. So, this approach, this is a simulation of a bow tie antenna, okay, what they are fabricating, and this shows the flexibility. Okay. So, this approach enables large area nano patterning with high throughput. The stencils are basically reusable and they demonstrate repeatable results with high throughput replication of the patterns. And the last important technique in this particular fabrication method will soft lithography. So, it is also an alternative fabrication method which allows multi-scale patterning of micro and nanoscale patterns on polymers. So, soft lithography is a typically inexpensive techniques that can overcome some of the disadvantages that you have seen during photolithography. So, this includes patterning the substrate below the diffraction limit and the need of high energy radiation that was there for photolithography. However, if you come to soft lithography, that typically requires a elastomeric, okay, which is fabricated by casting a PDMS onto a master substrate. So, we will discuss how it is done. So, the master features can be defined using the appropriate lithography technique for the pattern size. The stamp fabrication, which you can see here, is the first step, is completed by peeling off the PDMS. So, this is the feature, you put this material and then you peel off. Okay. So, you are basically peeling off the PDMS. So, this color code shows you what material is which one. Okay. So, this is the feature for transfer, and then you make this PDMS peel off, which has now got this feature embedded, right. Now, next method is called replica molding. So, replica molding allows for high resolution patterning of any polymer compatible with the PDMS stump, which can even include the polymers that are not photolithographically definable. Okay. So, the pre-polymer is basically applied onto a carrier, and the stamp is pressed firmly onto the surface. So, post curing and removal of the stamp, you can see here an inverted copy of the stamp is basically fabricated, which can be removed to form a freestanding design. Okay. So, here you can see that is happening, and in the last step, which is basically transfer printing, features of any desired material such as semiconductor, functional oxides or metals can be prepared on silicon substrate. So, this basically allows the use of established patterning techniques and high process temperatures. So, subsequently you can see the patterns are picked up by elastomeric stamps like this, okay, and placed onto the substrate of choice. So, you put it on the substrate, and then the substrate can then be released from the carrier. Okay. So, that is what you are getting the pattern transferred or printed on this. So, the transfer printing method is also very powerful, but it requires precise control over the adhesion of the features to the donor substrate, the stamp, as well as the target substrate. So, by using soft lithography techniques, the limitation of plastic substrates such as high temperature expansion, poor adhesion, low processing temperature and chemical instabilities can be overcome. Additionally, these particular techniques are suitable for a wide range of structure sizes and enable patterning of or patterning on non-planar surfaces as well. The last technique we will be discussing today is on EBL, E-beam lithography. So, it basically uses extremely small wavelength of a beam of electron at high accelerating voltages to obtain nanoscale patterns. So, analogous to photolithography, where a photoresist layer is exposed to UV light, in the E-beam lithography technique you require to expose the electron beam resist PMMA or Dept 520A by a high energy electron beam. Okay. So, this particular one is a very high performance positive electron beam resist, which show high resolution, high sensitivity and dry etch resistance. This causes a scission in the organic structure that is subsequently developed by using a standard developing solution, whereby the exposed region dissolves completely in the developer. Subsequently, deposition of metal and or dielectric layers will be carried out, following which the resist is dissolved to obtain the nanoscale patterns. So, this process utilizes the lift off process, or this approach utilizes the lift off process, and so the initial pattern defined by EBL needs to be the inverse of the desired pattern. EBL provides highly desirable ability to create nanoscale features below the diffraction limit of the standard photolithography processes, and it does not require a physical mask to transfer the patterns. For metamaterials, EBL technique is employed to fabricate sub-wavelength resolution resonators operating at optical wavelengths. So, this is mostly useful for optical metamaterial fabrication. The figure here shows a multi-layered metamaterial comprising of 4 layers of gold split ring resonators developed on a photoconductive polymer substrate PC403 using the EBL technique. While EBL is a powerful technique to achieve nanometer and submicron features, it has major limitations in creating large area and high performance metamaterials. For example, a right area of 3 mm by 3 mm would take up to 24 hours. So, large area patterning with multiple large area patterning with multiple stage moves resulting in poor resolution and stitching defects. So, stitching errors also hamper the ability to repeat the patterns over a large area without any misalignment problem. So, obviously, you can understand that there are long writing times due to the serial nature of the technique. Stitching errors will be impacting the periodicity and also low stability of the electron beam. So, additionally, the serial patterning process gives rise to issues such as instability of the beam due to drifting, and finally, the stability and the accuracy of the electron beam blanking are important factors that could also influence the effectiveness of this technique, right. So, with that we will conclude our lecture. We will take up discussion on basic electromagnetic theory and go into details of it starting from the next lecture. If you have got any query from this lecture, drop an email to this particular email address mentioning lecture number and the course title on the subject line. Thank you.